right, today's plan is to get through notes, work on the worksheet, and then even go over the worksheet before you leave today. Okay? We should have plenty of time to do all three of those things. All right? I have also decided that a quiz on Tuesday is not going to be on Tuesday. It's also not going to be on Monday. Okay. It's just like not going to happen. Sound good? Okay. So what that means is we do have a test next Friday. So we have a unit. Well, it was going to happen regardless. But that way we just have more time to go over stuff and review before the test. So we're just not going to have a quiz. Okay? So no quiz at all next week, but we will be testing next Friday. All right. So what we do today and tomorrow, or today, Monday, we'll just keep going. There we go. Here we go. Today is all about independence. So 2 events are independent if the outcome of one does not affect the outcome of the other. Right? Think about flipping a coin. On the first toss, what's the probability of getting heads? 50%, right? 1/2. 1 out of 2 of those sides is a heads. How about the second toss? Still 1 of those 2 sides is a heads, right? 1/2. What if the first one was heads? What's the probability of getting heads again? 1/2 again. All right? So, are the coin tosses independent? Yes. How come?
It's random.
We had the same chance every single time, right? The outcomes did not affect what was going to happen in the future. No matter how many times I flip a coin, there's still going to be a heads and a tails, right? It's not going to change. So they are independent events. Well, something else that you can think of that might be independent like that. A die. Olivia. She said me. Anything else you can think of might be independent?
Bingo.
Bingo? Well, no, bingo's not independent.
Oh, shoot,
It's not. Well, we'll talk about it. I'm happy you brought it up though. Dice, huh? A spinner. There we go. If you spin something, it doesn't like get removed, right? It's still there each time you spin it. Right?
Spin the wheel.
Spinning a wheel. Yep. Wheel of Fortune. Yeah, so Wheel of Fortune, each time they spin the wheel, it's independent, right? Yes. If the person next to you just got a bankrupt, that doesn't mean that you won't. It could still happen, right? Rock, paper, scissors, technically, is independent, yeah. Okay, so, what about a deck of cards?
No, it depends what game. Because when you put it in.
Okay, so it's kind of a yes and a no question. Let me ask you this. If I had a deck of cards, and I just gave Hannah one of them, what's the chances that that card is an ace? 4 out of the 52 cards, right? Is the chance that I just gave her an ace. Or 1 out of 13 if you simplify it. Okay? What's the probability that if I give her another card, that one's an ace? Okay. There's 2 answers here. Do I know what she got? No. I don't know what she got. What if the card she got to begin with was an ace? What's her probability of getting another one? 3 out of 51. What if it was not an ace? 4 out of 51. Regardless, didn't my chances change? Because my sample size changed, right? What if I gave her a card, she gave it back to me, I shuffled them up, and I gave her another one? That would be back to 4 out of 52. If I gave her a card, but she gave it back to me, and I shuffled and dealt again, it's the same circumstances, right? Mm-hmm. So her keeping the cards makes it dependent. If you're keeping something, it makes it dependent because your sample size has now decreased. Okay? If she gave me the card back before I gave her another one, then my sample size did not change. So it would be independent from there. So it does depend on if you keep it or give it back. Y'all know roulette, that wheel with the ball thing? They try to trick you at the casinos and stuff. They have a screen. What? It's not rigged. They have a screen that shows you like the last 10 spins for you to look at. So you might look up and be like, oh my gosh, there were 7 blacks in a row. The next one has to be a red number. Nope. Each spin is independent. Each and every one is independent. And there's even 2 green ones on there to really throw you off. Okay? So, but they try to trick you. They make you think there's patterns. No, there are no patterns. It is the same chances every single time they spin that wheel. Make sense? But they make you think there's something else going on. It's not rigged. It is not rigged. It is an independent spin every single time. Okay, so I want you to just go through these, see if you can figure out. You can talk or do it on your own. Which one of these would be considered dependent, and which ones would be independent? Your sandwich is oozing.
Oozing?
Something's happening there.
It's just PBJ. Not like
Looks like it's oozing a little bit. Nope.
Which one's which?
I'm not telling you. I got a tetanus shot yesterday, and now my arm hurts. Ugh. Ew. I got that one and the MMR shot. Measles, mumps, and rubella. And they took blood. Took like 5 tubes of blood out of me. Things we gotta do to make sure I'm healthy enough to have a baby. Gotta run the tests. It is good though. The bruise isn't that bad. I feel like barely see it. She did good. Alright, we good?
Yeah.
Okay. Alright. Here we go. Flipping a coin. What do we think? Independent?
Yeah.
I agree with you. Flipping a coin is independent. How about choosing a black 7 from a deck of cards, not returning it, and then choosing another black 7? Dependent. If you keep the card, you're changing your possible outcomes for drawing your other one.
Well, you give it back, it'll be independent.
Correct. So if you do not return it, it is dependent. Alright, pulling a blue M&M from a package of candy, then pulling out an M&M from the same package.
Dependent.
Dependent. Did you put it back?
No.
You did not put it back. It was dependent. A couple's first child having red hair, and then their second child also having red hair. Independent. Good. What your first child comes out as is not going to affect what the second child comes out as. They could both have red hair. There could be no red hair. The chances of red hair is the same each time. It's all about your genetic makeup. All right, we good? On independent versus dependent?
Yeah.
Now, there is an equation we could also use to determine if things are independent or not. So, if 2 events are independent, then the probability of getting both of them is the probability of one times the probability of the other. So yesterday we did the or, today we're doing the and. Okay? So if I am given the probability of 2 different events and the probability of their intersection, I can use those pieces to find out if those events were independent or dependent of each other. Okay. People such a
Y'all said the last couple days were easy. It wasn't my I don't like that.
Alright, here we go. Suppose it is known, remember this, 80% like Harry Potter, 30% are Twilight, and 20% are both. Okay, the question is this independent of each other? So we're going to use the math that they gave me. So, we want to know, does the probability of just Harry times the probability of just Twilight, does that equal the probability of them both? Okay, what's the probability of just Harry? What does it say? 80%, so what, 0.8? What's the probability of just Twilight? 0.3. They told me their intersection was what? Was 0.2. It's on the board. You don't have to remember. It's 20%, right? That's what they claim is true. But does 0.8 times 0.3 equal 0.2? Is that a true math equation? What is 0.8 times 0.3? 0.24. It is not. It is very different. Really? If something costs 21 cents, I can't buy it if I have 20 cents, but I could buy it if I had 24 cents. Right? True story. Alright, so since they are not equal, that's not true. These are not independent. These are dependent events. Okay? Nope. Not in this class. No sig figs.
I mean, either way, it still have to like, it wouldn't go up.
Yeah, she's trying to make you learn something. Alright, so do we understand? You have to have each individual and their intersection to figure out if they are or not independent. Alright, if they were independent, what would have been the probability of someone liking both? The 0.2. No, I lied. 0.24. If they were independent, then this should have been equal to the 0.24. So if they were independent, we were trying to get 0.24 out of it. But they told me it was 0.2, therefore it's not. It's better. It does. I'm not lying. Almost. So assuming they were independent, what is the probability of a randomly selecting student who likes Harry Potter and Twilight? Well, if they were independent, it would have been the 0.8 times 0.3, which is 0.24. All right, here we go. Bailey is working at her local clothing store. Based on past sales, the probability that the next item purchased will be a dress is 0.2. Put that up here. So probability of a dress is going to be 0.2. All right. Additionally, the probability that the next item to be purchased will be red, so probability of something red is going to be 0.3. Assuming that there are no red dresses, what does that mean? Is there a way to buy a red dress? No, there's not. There are none. The probability of getting a red dress is 0. They are not there. Are buying a dress and a red item independent? Okay, so we have to take each individual and multiply them together and see, do they equal their intersection? So what is 0.3 times 0.2? 0.06. No, that's kind of what we're doing. Does that equal 0? No, it does not. So are these independent events? No, they are not. They are dependent events. Think about it. If I buy something out of a store, regardless what it was, shoes, red, anything. If I buy something and I leave with it, haven't I changed the sample size of what's left in the store? Kind of like if Hannah got an ace or didn't get an ace. It didn't matter what she got, but it affected what the next card was going to be, right? Because there was a card missing in the deck. You buy something and leave, there is something else missing from the store. Make sense? Why that was dependent and why that open. All right, what is the probability that the next item purchased is a dress or it's red? So that goes back to yesterday. The probability of red or a dress. Remember that? So probability of red plus probability of a dress minus the probability of a red dress. So what was the probability of something red? 0.3. Probability of a dress was 0.2 minus the probability of a red dress, which was none. That gives me 0.5. So the probability of someone coming in and buying something red or buying a dress is going to be 0.5. So buying something red, buying a dress. This is the or part. This was or. Up here, this was and. So now we have two different equations. One's for and, one's for or. Questions? All right. Move on to the next situation. Here we go. Mike makes 85% of the free throws that he attempts in basketball. Suppose Mike gets 2 free throws, and his free throws are independent. So this time we're telling you already they're independent of each other. Draw a tree diagram of the possible outcomes. It's okay. Determine the sample space and find the associated probabilities. How many free throws is he taking? 2. So my tree isn't going to be that big, so calm down. Okay? What's the outcome if he shoots a free throw? He's going to get it or he's not going to get it, right? He's going to make the basket or he's not going to make the basket. So his first attempt, those are your only 2 outcomes. Okay? Let's say he threw the first one, he makes it. What are the 2 outcomes when he throws it again? He can make it or miss it the second time, right? So he can make it and make it. He can make it then miss then make, or miss and miss, right? How many total outcomes is that? There's 4 total ways that he can shoot the basketball. Okay, so yes, the tree, but it's not as bad as the Harry Potter Hogwarts cluster from yesterday. All right, they gave me something else. They told me, what is his probability of making the shot? 85%, so 0.85, right? So what does that mean about his probability for missing it? 0.1, right? Because you can only make or miss, so doesn't that have to give you 100% of your shots? So 0.85 plus 0.15 gives you that probability of 1. All right, this is what we're going to use to help me with my 4 different probabilities. So what's the percent of making a free throw? Of making it. No, for Mike specifically, it's 0.85, right? And then how about him making it again? 0.85. So we're combining this and this, so we're going to multiply them together to get 0.7225. So each time he makes it, that's 0.85. So 0.85, 0.85. All right, how about making it, but then missing it? Well, we just said his probability of missing it was 0.15, right? So how's that going to get set up? Which gives me 0.1275. So the probability of him making both shots is about 72%. Probability of him making the first but missing the second is about 12%-ish. How about if he misses the first one, so that's 0.15, but he makes the second one? It's going to be the same thing, right? He just missed and then made, so it's just flip-flopped. And then what's the probability of Mike missing both shots? Only 2% chance that he misses both of them. That's pretty good. It's like Mike of basketball is like Dom of football. They're both wonderful. Alright, so that tree wasn't that bad, was it? No. Alright, we're going to answer some questions about it, and then it's worksheet time. Okay? We've got a couple more questions about Mike and his free throws. So, what is the probability that Mike makes both free throws? That's an and, right? That's a make and a make. So was that on my tree? Yes, it's a combination of the two. What was it? Yep, roughly 0.7225. That was a make and a make. All right. What is the probability that Mike makes at least one free throw? At least one. So that means he makes the first basket or he makes the second basket. So this is an or equation. This is or. Makes at least one. So he makes the first or he makes the second. So what's the probability that he makes the first one? 0.85. What's the probability that he makes the second one? 0.85. And what was the probability of making both? 0.7225. Add and subtract. Probability of him making at least one of those baskets is 0.9775. So real good. Real good probability he's going to make one of them. Remember, he's the Dom of basketball, so it's going to be great. Okay, if Mike makes the first free throw, what's the probability that he makes the second free throw? 0.85. Good. Does it matter if he makes it or not the first time? That does not change his probability. So because they're independent, each throw he has the 0.85 probability of making it. All right? Still feel okay about it? A little bit. All right, I got a worksheet for you to do. You, again, will probably have time to get it all done. I would love for you to be done before like 12:45, 12:48-ish, so we can go over our answers together. All right?